So we are going to part 3 of our course, and this is actually the most interesting part of the entire course. So if you recall, what we have done in part 1 is that we learned some overall pipeline, and in part 2 we spent a lot of time talking about methods. Okay, and but you can always go online and find more methods that are not covered in this course, and you will be able to find an increasing number over the time that of your entire career, right? And so what would be the common principles behind all these methods? Is it something that we can learn in general? So part 3 of our course is going to address the question of how much can a method do in the context of learning. And so we will start this series of discussions by first telling you that there are indeed some problems that machine learning cannot help you. Okay, I'm going to give you a bad news first. And I want to explain to you what would be the things that you will really need to expect to have in your problem in order for machine learning to work. Okay, the thing that I'm going to talk about will be extremely general, that it applies to all these classical methods, the linear methods, and it also applies to deep neural networks. It just works for all kinds of machine learning algorithms. We will be using the linear models from time to time as illustrations. The reason is that it's easy to analyze, and we want to know about what would be the performance. Okay? However, the thing that we are going to study is really, really general. So, I want to start by telling you the agenda of this part of the entire course. So this is part 3. Part 1 and part 2 we have gone through already. Part 3, we will ask the following set of questions. Now that I have a method, so what? Okay. Will it do well, or how well? Right? So now you have a method. Imagine that you have a support vector machine. It returns you certain classification rate for this particular testing data set. You feel happy, and then you bring it over to another testing data set. It completely fails, and then you cry, and then you ask why. What has happened? Okay. So will it do well? How well? Will it fail? When will it fail? Under what conditions that it will fail? It has to be extremely general. We need to put some assumptions into the entire data set to say something so general. Of course, it has to do with the model, okay, and it has to do with how complex the model is. If you have very, very complex data sets and you are using extremely simple model, probably it's not going to work. Vice versa, if you have a very simple data set but you use extremely complicated model, maybe you're overkilling, and what would be the price that you need to pay? Having more sample, does it mean better? And how many samples will be needed in order to achieve certain performance guarantee? That's also extremely relevant. I have 10,000 images in my data sets. Is it good enough for the problem that I'm encountering? Versus I have only 10 images, but if my problem is a lot simpler, maybe that's enough. So what would be the required number of samples? That's fundamental. Can every problem be solved by learning? That's even more fundamental, okay? Under what assumptions that you need to make about the data so that the learning will make sense? Is there any cases that counter examples where the learning will just completely fail? What should you do when you overfit? Typical question, right? How do you avoid overfit? That's a very practical question too, right? So this part of the course, as you see, that we are not just looking at one specific method, because by now, I believe that you have already had enough tools in your pocket. They're not the best tools, because you can go online and find better tools. But they are tools. They're pretty useful tools. And you can ask these set of questions. And by answering these set of questions, you certainly gain a lot of insights about when it goes to your own problem, what will happen. Can you generalize these ideas to the problems? Okay. So here's the outline of today's lecture. we want to ask 3 questions. One is, what constitutes a learning problem? What would be the ingredient of a learning problem? And then I want to show you example and discuss whether learning is fundamentally feasible or not. Not all cases are feasible. Some cases are feasible. I want to explain this very clearly. And then I want to introduce this notion, training versus testing. Now, not the thing that you are doing on your program. Okay? Everyone knows what is training, what is testing. But I want to define it very, very carefully. And then we want to study this training and testing in really, really great deep. Okay? So that you can really understand what is the difference between training and testing. There's a small subtle difference, but that subtle difference is enough to cause big failures. Okay, and then now this is the reference. I only have one reference for this lecture. And in fact, for the entire part 3 of the course, we'll be using this book, okay, Learning from Data, and then we will go over several chapters in this book. And today's lecture is based on chapter 1.3. You're highly encouraged to take a look at that book. Okay, so to start with, I want to introduce notations. This set of notations will be used over and over for the entire part 3 of our course. So I will have a set of data points. They are labeled as x1 through xn. So each xi will be a high-dimensional vector. It could be an image. It could be a speech file. So it's a high-dimensional vector. Yi through yn will be the labels. And for simplicity, I'm going to assume that it will be binary. Okay. And then all these xi, x, and yns, they will form a thing called a training data set. So these data sets will be a set that contains all these pairs of xn and yns. So n going from 1 to capital N. So this is the training data set. It contains all the pairs. Each pair will contain an input vector, and then you have a label. And then there is a thing, it's a magical thing, it's called the target function. The target function is going to take an input and give you a label. This is done by some unknown creature, okay? And then there is this is just the ground truth mapping from a label, from a input to a label. So I give you an image. You look at the image, you say that this is a dog, or this is an orange, okay? Now, why? Well, because you are that unknown creature, because you know the ground truth. This is a dog, this is an orange. Okay, we assume that there's a mapping. Now, I don't just want to call it xn and yn. I want to put an explicit mapping saying that yn equals to f applied on xn. Okay, so for every xn, and if you apply the target function, that is going to give you the ground truth label. Now, this function, target function, is of course unknown to you. For otherwise, there's no problem. If you know the target function, then if I give you an input vector, you can just tell me the label. There's no learning required. So f is unknown. So pictorially, what happens is the following. You have a set of data points, and then you apply this target function. The target function will map them to either +1 or -1 in a binary case. And so you have this very simple relationship: yn equals to f of xn, label, input, and then the target function. So what would be the learning problem? Well, now you can imagine that the learning problem would be very simple. I give you xn, I give you yn, I give you the entire training set. I ask, what is the f? Right? Because if you find the f, the problem is solved. But certainly the problem is difficult because you only have a finite set of training samples. And now I ask you to find a very, very big F here. And the big F can be extremely complicated because why is this image a dog versus why is this image an orange? How do you know why isn't a tiger? Why isn't it an airplane? Why, right? So this F can be extremely complicated. If you think about the decision boundary, what you're doing is that this F is going to assign all these samples into two classes, +1 and -1. And this decision boundary can be extremely complicated. Who say that it has to be a straight line? It can be a curve, right? So you just don't know. And so what you're doing is that you're saying, look, by given this data set, I'm going to find a maybe linear model. And so I am going to find a line that approximate this decision boundary. And because of this approximation that you're doing, you will never be the same as your F. And so you make error, and you want to quantify this error, right? So you see that in this learning problem, the only thing that's given to you is the data set. And then your goal is to learn this crazy function called F. And it's impossible to believe that you can learn this F, right? So we want to understand in what conditions that you can actually find this F, and how close can your estimate be compared to this ground truth F. So that would be a meaningful learning question to ask. I also want to separate the training sets, the data sets into two halves. Okay, so let's think about this is the entire population of your data points. Okay, by population I mean that the collection of all possible images in the world, and inside which you have an extremely small set that's called an image net, and that contains 1.28 million images. That is your training set. Okay, and now you're training your ResNet 50, and then you want to apply it to images that are not inside your ImageNet data set. Then you're looking in the testing set. So in this drawing, you can see that I have an extremely big thing. This is called the population set. Okay, this is actually not D. This is the population set. This contains all the possible training and testing samples, within which you have a small subset. It's called the training set. And the training set, I also call them the in samples, inside the training set samples. Anything that's outside the training set is called the testing set. And I call them the out samples. So when you try to enter any competition of deep neural networks, normally what you will see is that I have a big portion of data that is called the training set, and then there is a small portion of the data is called the testing set, and then all your scores will be defined by this testing set. Okay, so you will normally have a thinking that training set is usually bigger than the testing set. Now, the reality is, this is your training set, and this will be your testing set. See the difference? Okay? This is what you are doing when you write a paper. This is what you do when you go out to the world and then you solve a real world problem. It's very different. Okay? Now, why is this the problem? Because you have 1.28 million data sets. Fine. Okay. But that's only 1.28 million. You ask, how many images are there on the internet? There's about 1 billion per day in Facebook. Okay. You can check the statistics. This is already outdated. Okay. Now it could be 10 billion images per day. And then you're training on 1.28 million images. And then you want to generalize. You are looking at this problem. And then the reason that you fail is because you only report your accuracy here. And you feel happy, but then when you bring it out, you cry because it's a whole different problem. Okay, so this is the difference between training and testing. You need to understand the role of training and testing. One is called the in sample, the other one is called out sample. They have to share some kind of properties in order for you to run your learning algorithm. Okay, so far so good, right? Now, let's also define a term called the hypothesis set. This is a set that contains all the possible decision rules that you are going to employ. This set can be finite or it can be infinite. Like what? If you think about a linear classifier, you have two parameters, but then you have infinitely many choices of these two parameters, and therefore, how many hypotheses that you can construct? Well, you can, let's say this is your data set. You can say, I'm gonna cut it into two halves using a linear classifier. That would be one hypothesis. That can be another hypothesis. This is a hypothesis, although of course this is a very terrible hypothesis, but it's still a hypothesis, right? So as long as you specify the family of hypotheses, you will have a collection of things called a hypothesis set. Now, what your learning algorithm is going to do is that you are going to look at your training data, this very small set called a training set. You are going to look into this hypothesis set. You will say, among all these M hypotheses, which one should I pick? Now, you may pick a hypothesis using this parameter. This is a linear model, a two parameter. I'm picking parameter 1 being 2.5, parameter 2 being 0.8. Okay, that means you're picking one of those in your hypothesis set. Okay, this is a learning algorithm. The learning algorithm says, give me the data set. Among the data set, I'm going to choose a hypothesis for you. That would be the best hypothesis that I can do, constrained to the family of hypotheses that you allow me to choose. Now, of course, you can say this hypothesis set can be extremely big. That contains linear, quadratic, higher order models. Which one should I choose? Well, that's up to you. Okay, so you need to specify upfront what model you want to use. If you choose to use a 50-layer deep neural network, this set will contain all the possible configurations of the 50-layer deep neural networks. By configurations, I mean that changing the parameters, changing the weights of the neurons, changing the weights of the the edges. Okay, so that would define the choices that you have. So you need to first pick a model, and then among the model, you specify what are the tunable parameters. The tunable parameters will define this hypothesis set. Okay, now once we run this hypothesis, then this learning algorithm, you will be able to find something called a final hypothesis. This is the hypothesis that you have decided to use. And the decision is based on just the training set. You are not allowed to go to the testing set and then just look at that one sample and say, okay, I want to change. You cannot do that. You can only look at your training set and then you want to make a decision. Once your decision is made, you need to submit your code to the organizer and then let them evaluate. It's not like when you write a paper that you train it on here and then you test it on here, not good, and then you retune it and then you retune it until it looks good. You cannot do that, okay? Once you are done, you will report your final hypothesis. Once you report your final hypothesis, you cannot do anything. Okay? Alright. So this is the picture that you have data points. This is the ground truth unknown target function that can separate your data set into two halves. The decision boundary can be highly nonlinear. You just don't know. Here I'm choosing among all these possible hypotheses, and in this example, they are all the linear models. I can have good hypothesis. I can have bad hypothesis. It really depends on which one I pick. Okay, and by which one I pick, I mean that which one that your learning algorithm is going to return you after looking at your training data set. This is the model that describes everything that we need to know about this part of the course. It's called the learning model. This is a little bit complicated in the first time if you read it. It has a lot of components. Okay, so let me walk through it with you once, and then let's walk through it again and again over the following weeks. Here is the starting point. You have a training data set that contains all the training samples. This training data set does not come from nowhere. It comes from the target function. So there exists a target function that can map the input vectors to a label. Okay? So that is the generative process that goes from the target function to the training data. And then you, as a user, you can specify the hypothesis set. For example, you say that I want to work with linear models, then you have constrained yourself to a set of linear classifiers. From there, you look at these two, you are going to apply something called the learning algorithm. That can be a perceptron algorithm, that can be a SVM, that can be a logistic regression. That is your choice. So you are going to choose a learning algorithm, including the stochastic gradient descent, CVX, whatever the pipeline that we have introduced. That is the learning algorithm. And then you're going to report the final hypothesis. And of course, what you want is to make G as close to F as possible, because F is your ground truth. You want your predicted classifier to be similar to F. There is something interesting here. It's called the unknown input distribution, which I have not introduced yet. Okay. However, this unknown distribution is going to do a extremely important magic that will link this training data set and the testing data set, which I'm not specifying here yet. Okay. So this P of X is a probability distribution, and all the samples, the training samples, will be drawn from the probability distribution. At the same time, your testing sample should also be drawn from the underlying distribution. If this input distribution is missing, then you will run into some very, very funny situations that I'm going to explain shortly. Okay? This is a very important piece of the model, and in fact, this is the most important piece of this model to work.